we've been talking quite a bit about the relationship between rate law, mechanism, and the path that a reaction takes to go from reactants to products. In the last segment, we saw an example of using some experimental evidence to determine the rate law, and thus the mechanism, for a substitution reaction in which some T-butyl chloride reacted with hydroxide to form T-butanol. I wanted to take just a moment to look at the potential energy surface for that reaction, and in particular how that mechanism and rate law told us about the reaction that was taking place. So, our products were more stable than our reactants. The reaction was going forwards. So, in this particular reaction coordinate, you can see that our reactants are higher in energy than our products. That amount is related to, although for reasons that you'll learn about in more advanced courses, not quite the same as the delta G we would expect for a reaction. So you can see in this case, the delta E for the reaction is less than 0. The reaction is becoming more stable. We also said that in that last reaction, the first step of the SN1 reaction, in which the bond between the carbon and chlorine broke to form a cation and an anion, that was a relatively slow step, and thus the rate determining step. Well, in our potential energy space, that is equivalent to a step with a very large activation energy. This is a difficult hill to climb over. After climbing that hill, we reach a set of intermediates. In this case, the carbocation, the chloride, and the hydroxide floating around. Now you can see that these intermediates, by comparison, are less stable than the reactants. Intermediates could be at all sorts of different energies relative to the reactants. In this particular case, though, it should hopefully be intuitively apparent to you that a carbon that only has 3 bonds to it and no other electrons is not going to be particularly stable. So this intermediate doesn't exist for very long. But it now has 2 possibilities. Once the reaction has reached this intermediate, it could go backwards to the first step or forwards on to the products. If it were to go forwards, it would now have to pass over this barrier. This second barrier has an activation energy, Ea2. We said that this reaction should be relatively fast because a anionic hydroxide moiety is attacking a cationic carbon center. That's symbolized by a lower barrier height. I also want to be really specific here to point out that the peak we're comparing with here is relative to the intermediate's energy, and we're not worried about the energy of this particular state relative to the reactants. You can think of it a little bit like maybe base camp on the course of a hike. How it feels to hike a hill is going to depend on where you woke up that morning, in essence. If you're already halfway up, it's not quite so bad. You could think of that intermediate a little bit like base camp on the way to the top of Mount Everest. So, in this case, Ea1 is greater than Ea2. So step 1 is the rate determining step. The reason that this reaction goes forwards is because if it were to try to go backwards, the products would have to climb backwards up this hill. Climbing backwards, the products would now be going up something that has this very, very large energy. And because that energy is so large, it's too difficult for the products to climb backwards and the reaction to reverse.